This rapidly expanding web of nodes represents the exponential growth of data context. In 2026, this growth has collided with the physical and economic limits of inference costs. Engineering teams have pivoted to a specific problem, making 1 million tokens of state computationally affordable. Scaling raw model weights, adding more parameters, fails to solve this memory bottleneck. Pushing massive context through a standard dense architecture consumes more VRAM than modern hardware can efficiently serve. Solving this requires a hardware-software co-design. This is the 2026 Agentic node, a multi-tiered architecture where the model and the external software environment are designed as a single system. We are going to build this frontier AI stack from the base up to see how these tiers interact, covering extreme sparsity at the foundation, divergent attention in the middle layer, stabilized residual plumbing, and external multi-agent orchestration. Achievable frontier performance now requires optimizing this entire vertical stack, rather than focusing on the neural network in isolation. At the foundation, labs have converged on a single strategy. The feed-forward network must utilize an ultrasparse mixture of experts architecture. This is the architecture of Kimi K2.6. It contains 1 trillion parameters, partitioned into 384 distinct expert clusters. As a token passes through, the router selects only 8 experts. The model activates 32 billion parameters, while the remaining 97% remains dormant. This retains a trillion parameter capacity at the compute cost of a 32 billion model. Qwen 3.6-35b pushes this further, activating only 3 billion parameters, giving mobile-class inference speed while holding flagship weights in VRAM. This allows developers to serve high-quality outputs at high tokens per second, even when the model is handling long context windows. Standard components like rope, swig-glue, and RMS norm surround this MOE base, providing the mathematical stability needed for training. Extreme sparsity is the prerequisite that makes processing million-token contexts computationally viable on modern GPUs. While MOE is the consensus for the base, labs take different paths in the attention layer. This is where the architectural designs actually diverge. The common enemy is the KV cache bottleneck. Storing key and value vectors for 1 million tokens require hundreds of gigabytes of memory, often exceeding the capacity of a single compute node. One solution is latent attention, or MLA. Large uncompressed KV vectors are funneled toward a narrow latent bottleneck. MLA squashes these vectors into a low-dimensional space. By storing these compressed summaries in the cache, the model reduces its memory footprint by up to 90%. This compression increases computational intensity during the inference pass, essentially trading flops for memory savings. A second path is hybrid linear attention. This architecture alternates standard attention layers with recurrent loops based on gated delta net. Integrating recurrent layers changes how state is stored. The model needs a constant amount of memory to process more tokens, rather than memory usage increasing quadratically. Qwen uses this to halt memory explosion, but Minimax argues standard attention is more reliable for multi-turn reasoning and agentic tasks. DeepSeek V4 introduces compressed sparse attention, segmenting context into 3 memory tiers. It keeps exact data for recent tokens, compresses distant tokens, and uses sparse retrieval in between. This tiered approach reduces flops by over 70% at 1 million tokens. Each of these 3 paths represents a different engineering trade-off to enable sustained reasoning across massive context windows. In 2026, architectural innovation has moved deeper into the residual stream that connects the layers of the network. DeepSeek V4 introduced a significant change here by modernizing the residual pathway itself. This bold bypass line is the residual connection. It allows data signals to skip over the attention and FFN blocks. The MHC mechanism widens this channel by a factor of 4. To maintain stability, the signal passes through a filter constrained to the Birkhoff polytope. A gauge locks the signal's spectral norm perfectly at 1 as it passes through. This prevents the signal from either exploding into high-frequency noise or vanishing into nothing across a trillion-parameter stack. Controlling this internal signal flow is the primary reason trillion-parameter models can now be trained without the massive loss spikes that plagued earlier systems. The final layer of the stack sits outside the model weights. This is the orchestration scaffold. The performance of a model on agentic benchmarks depends as much on the external harness as it does on the underlying neural network. As this crystalline core fractures, we see the transition to parallel execution. A single high-level goal is now handled by specialized agents working in concert. A prompt hits a central orchestrator node, drawing connecting lines to various worker nodes. Operating in parallel with distinct contexts circumvents the memory limits of a single model. As these agents complete tasks, they store results in 3 memory cylinders: episodic for specific events, semantic for knowledge, and procedural for skills. This tiered memory allows the system to recover from worker failures and learn from past interactions over time. The neural network provides the raw reasoning, but this orchestrator-worker hierarchy is what enables the system to execute reliable, autonomous actions. Closed labs and open-weight ecosystems take different approaches to assembling the stack. Closed systems like GPT 5.5 integrate these agentic objectives and multimodal flows directly into the pre-training phase. The model is trained to plan and use tools from its first trillion tokens. Open labs like Kimi rely on massive synthesized data pipelines and joint reinforcement learning to teach the model to operate within a complex software harness. We have now assembled the full 2026 stack: an extremely sparse MOE base, specialized long context attention, stabilized residuals, and a multi-agent orchestration layer. In 2026, the competitive advantage lies in mastering the orchestration systems that direct and harness the model's activated compute.